So the aim of this podcast is to give you practice in calculating the curl of a vector field, and there are 3 such exercises, and also to show an identity which the curl and the gradient satisfy. So what you should do is write down the questions, tackle them with pen and paper, and then you can come back, look at the next slide, see if you've got the answers right. If you have, well done, and if not, you can use that feedback to move on to the solutions which follow and understand the questions better, and then you can come back and tackle this video again in a month or so and see if you can do them then. Okay, so you should now write down the questions and come back to the video later. Okay, welcome back. Let's move on to the next slide and look at the answers to all of these problems. So here are the solutions. When you calculate the curl of this vector, what you obtain is a vector pointing in the I direction, and this is the coefficient of it. The curl of the radial vector, the position vector, xi plus yj plus zk, is 0, and the curl of this vector, where r is the magnitude of the position vector, is found to be this, and to do that you needed to use the chain rule, and you were asked to show that the curl of the gradient vanishes. So if you've got the correct answers, well done, and if not, on the next few slides I'm going to work out the detailed answers to each of these problems. So let's move on to the answer to this first question. So to solve the first problem and calculate the curl of this vector, we recall the definition of the curl, and we write this determinant-like structure where the first row are the unit vectors I, j, and k, the second row are the derivative or partial derivative operators d by dx, d by dy, and d by dz, and the bottom row are the components of the vector whose curl is being calculated in the I, j, and k directions. So in the case at hand, what we have to do to calculate the curl of 2x squared I plus z squared j minus y cubed k is to write out this determinant-like structure I, j, and k. I'm giving myself a bit more room so that I can write out the components of the vector, d by dy and d by dz, and on the bottom row we have 2x squared, because that is this component. The next component is z squared, so I put that here, and the final component is minus y cubed. So now we expand this determinant along the top row, and what we obtain is I times d by dy acting upon minus y cubed, d by dy acting on minus y cubed, minus d by dz acting upon z squared, close the brackets, and that's this term minus this term, this acting on this, and then we go to the next term and we put down a minus sign, and now we take this acting upon this minus this acting upon this, and so we have d by dx acting upon minus y cubed minus d by dz acting upon 2x squared, close brackets, and then we have plus k, and for this component we ignore this column and we have this acting on this minus this acting on this. So we are going to have, open brackets, d by dx on z squared minus d by dy acting upon 2x squared, close brackets, and this is our result. We just have to carry out the partial differentiations. This we see as non-zero, this is non-zero, this will vanish because this purely depends upon y and we are differentiating with respect to x. In a similar way, this vanishes, it depends upon x, and this is the partial derivative with respect to z. This will vanish because it's the partial derivative of z squared with respect to x, and this vanishes because, again, we're differentiating here with respect to y, and this does not depend upon y. So I'll just pause, make myself a little bit of room. So what we obtain is that the curl of 2x squared I plus z squared j minus y cubed k is equal to, from the first derivative we're going to get minus 3y squared, from here we're going to get minus 2z, so both of them have a minus sign, so I'm going to pull out the minus sign, and it's 3y squared plus 2z, close brackets, multiplied by the unit vector I, and as we said, everything else vanishes. So this is our result. So everything followed from the definition, calculating the partial derivatives and expanding this determinant in the standard way, being careful about minus signs. So with that we're going to move on to the next answers, but I'm not going to write out the definition as explicitly on the next few slides, just to save a little bit of room. So the next question was to calculate the curl of the position vector, and to do that we just recall our definition again that was written on the previous slide. So we are going to expand here I, j, k, d by dx, d by dy, d by dz, and the bottom row are the components of the vector whose curl is being calculated. So this is x, y, and z. So x, y, z. So what we get in the, sorry, I missed a underlining this vector here. What we get is, in the I direction, it is d by dy acting on z minus d by dz acting upon y. And this will vanish because this does not depend upon y, and this does not depend upon z. And similarly, we are going to obtain in the other directions minus sign here, minus, and it's d by dx acting on z, which will vanish because z does not depend on x, minus d by dz acting upon x, plus k multiplied by the derivative with respect to x of y, which vanishes, minus the derivative with respect to y of x, which also vanishes. So every component vanishes, and what we see is that the curl of R is 0. And with that, we can move on to the next slide. So the third question asked us to calculate the curl of this vector, where R here and here is the magnitude of the position vector. It is the square root of x squared plus y squared plus z squared, so it's the distance from the origin in 3 dimensions of the point with vector xi plus yj plus zk. Okay, so let's calculate this. So we need to calculate the determinant, top row I, j, k, d by dx, d by dy, d by dz, to make this x a bit clearer, and it is e to the minus r, e to the minus r, and 2. So when we expand this in the I direction, we are going to have d by dy on 2, so that's going to vanish, minus the derivative with respect to z of e to the minus r, so that corresponds to this acting on that, minus this acting on that, minus, and in the j direction it is d by dx acting on 2, so that will vanish, minus d by dz acting on e to the minus r, and then plus k times d by dx acting on e to the minus r, minus d by dy acting on e to the minus r. So as stated, this and this will vanish, and all of the other terms are going to involve these derivatives of e to the minus r. So let's just very quickly work out what that derivative is going to be. So note d by dx, for example, of e to the minus r means the derivative with respect to x of e to the minus, and it is x squared plus y squared plus z squared, all to the power of a half. Now, the derivative of an exponential is an exponential with its argument unchanged, so I can write that for brevity still as e to the minus r, times the derivative of the argument. So that is d by dx of, and the argument was minus r, or minus x squared plus y squared plus z squared, all to the power of a half. So now, when we differentiate this, we're going to pull the half down, reduce the power to minus a half, and then we're going to multiply by the derivative of the argument here, which will give us 2x. So putting all of that together, what we get is d by dx of e to the minus r is going to be, well, there is a minus sign. We are going to get the x from the 2x, the 2 and the half will cancel. X squared plus y squared plus z squared to the minus a half means 1 over r, and then we have this factor of e to the minus r, which multiplies everything. So this is our derivative, and by symmetry we can immediately write out what the others are. So symmetry tells us that d by dy of e to the minus r is minus y over r e to the minus r, and d by dz of e to the minus r is minus z over r e to the minus r. And if that's not immediately apparent, you can work them out and see that this is true. So now we have all of the derivatives that we are going to need, and we can write out our answer. So what we obtain is the following: the curl of e to the minus r I plus e to the minus r j plus 2k is equal to, so here we have minus this derivative here, minus times minus is plus, so we are going to get z over r in the I direction times e to the minus r in the I direction. The next term, we have a minus sign here and a minus sign here, so we have a plus sign, but then that's multiplied by this same derivative, so we pick up a minus sign overall. There are 1, 2, 3 minus signs, so we obtain minus z over r e to the minus r j, and finally here we get two contributions, and this one is going to have a minus sign. This one, minus times minus, will be plus, so I'm going to write this term first with the plus sign. So what we obtain is plus open brackets y over r times e to the minus r minus x, so I can put that all on a common denominator, y minus x over r times e to the minus r, and then the unit vector k. And this is our answer for this curl. So what we did again was we used the basic definition with this vector substituted in here. We expand it out, being careful about minus signs. Two of the derivatives were 0, and then the other derivatives we needed to calculate this using the chain rule, and then by symmetry, because r is symmetric under exchange of x and y, say, or y and z, we can immediately write out the other derivatives, and as stated, if it's not obvious to you, calculate them and see how it works. And then we just substituted these results back into here, and this gave us our answer. So with that, let's move on to the final answer. So on this final slide, what we want to do is to show that the curl of the gradient of a scalar field f, which is differentiable twice, is going to vanish. So we know what the gradient is. Let's just write that down. So recall that the gradient of a scalar field is a vector d by dx of f I plus the derivative with respect to y of our scalar field j plus d by dz of our scalar field f k. So we have the gradient, which is a vector operator, and this is the vector field that it generates from a scalar field f. We also remember our definition of the curl that we have used repeatedly in this video. So let me just write it down. Also, the curl of a vector field, let's call it A, is, and it's I, j, k, d by dx, d by dy, d by dz on A1, A2, and A3, where, as previously used, these are the components of the vector field in the directions I, j, and k. Okay, so let's now just take this and substitute it into here. So this is the field whose curl we are going to calculate. So A1 is going to be df dx, A2 is df dy, and A3 is df dz. So A1 is df dx, A2 is df dy, and A3 is df dz. So therefore, the curl of the gradient of the scalar field f is going to be given by I, j, k, d by dx, d by dy, d by dz, acting upon df dx, df dy, df dz. And I'm going to pause here and make a little bit more room so that we can see explicitly how this works. And what we obtain is, in the I direction, I times, so now this derivative acts upon this, and then we subtract this derivative acting upon this. So we're going to have d2f, or the derivative with respect to y, on the derivative of df dz, minus, and then it's d by dz on df dy. So that's what we get with this acting on this minus this acting on this. And then I'm not going to write out the other components explicitly, but I will just put plus dot 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 for the other components. You can calculate them and see that it works in the same way. Now, by equality of mixed partial derivatives, we recognize that these two terms are the same. So if I have f and I differentiate it with respect to z and then differentiate it with respect to y, it is the same as if I take f and I differentiate it first with respect to y and then with respect to z. So if f obeys the conditions that we can exchange the order of the differentiation, this will equal this. So what we get is the curl of the gradient of f is going to be 0 from the equality of mixed partial derivatives. And that is the result that we had to calculate. So with that, we have completed the answers to all of the questions, and I hope that this video has helped you. Thank you.